In this video, we will have the proof of theorem 5.3.1 as in 10, which states that if p of x is a member of fx and is of degree n, where n is greater than 1, and if it is irreducible over f, then there is an extension e of f such that degree of e over f is n and the p of x has a root in e. So in this case, we are given p of x to be about p of x, its degree is n and it is irreducible over f. Irreducible over f. This is given. Now what we need to prove is three things that we need to establish. First one is there is an extension field E, and then degree of E over f is n. And finally, this p of x has a root in, it has a root in E. So these three things that we need to establish, we are given p of x to be of degree n and that's irreducible over f. Now we will consider p of x to be the given irreducible polynomial of degree n over f and v be the ideal generated by p of x. Now p of x is irreducible, so by the last lemma in that polynomial rings, we conclude that v is maximal in fx. So because v is maximal, this must be a field. So now you take this fx mod v to be E, which consists of elements of the form an element from this and plus v. So f of x plus capital V, where f of x range over capital Fx, and we consider f closure, f bar we shall call, f bar, which is a collection of all constants. See, the first one should be a polynomial. Here we are considering constant. Any constant is a polynomial of degree 0. So f bar we consider as this collection. So you are taking E as this and f bar as this. Now first we need to prove that this E is an extension of f. So for that you define a mapping, say psi from f to f bar in this way. It takes any scalar here to f bar is this collection, so you have this. So in this way you define your psi. Being defined by us, we have to check whether it is well defined. So for that you consider two elements in the domain to be the same, namely alpha and beta to be equal. Obviously alpha plus v is equal to beta plus v, and that in turn gives the image of alpha under psi equals the image of beta under psi, and therefore psi is well defined. Next we consider to prove one-to-one we consider alpha psi to be equal to beta psi, and that gives alpha plus v equals beta plus v. And from here we have, this is from one of the results from BSc, that even in groups, that's a very famous result, that HA equals HB if and only if AB inverse belongs to H. The same way in the case of vector spaces, if you have v plus w to be equal to v prime plus w, then v minus v prime should be in w. This is if and only if condition. So that is what is used in the case of fx mod v also. So this in turn gives alpha minus beta belongs to v. So you have same thing is again written. So you can write v, this one as alpha minus beta equal to p of x into f of x. Why it is so? Because v is generated by p of x. We have taken v is generated by p of x. So any element belonging to that should only be of this form. Now this one is of degree 0 and here you have this to be of degree n. So how can we equate these two unless you have your f of x to be 0? So because f of x is non-zero, degree of LHS is 0, but degree of RHS is greater than or equal to n. So that is not possible, which forces us to conclude that our f of x should only be 0. So here when f of x is 0, that is appearing here, so your alpha minus beta will be 0. So that in turn gives alpha equals beta, and so psi is 1 to 1. Now psi is obviously on to, because to every alpha over here you have alpha plus b. So any element here in our f bar is only of this form. So obviously alpha act as the preimage. So the psi is 1 to 1 on to, and then now we are going to prove that it is a ring homomorphism. So we consider our alpha plus beta. See, what is your psi? Your psi is a mapping from f to f bar, f to f bar. So here we consider, we are treating now, even though it has even the vector space format, here we are not checking, every field is also a vector space. So here we are not checking vector space homomorphism. Now, being field, they are rings, and therefore ring homomorphism is only checked. So you have alpha plus sum and then product. So you have alpha plus beta psi. You need to prove that to be alpha psi plus beta psi, and alpha beta psi to be alpha psi into beta psi. So you consider LHS, and that is what is written here. And this is nothing but alpha plus beta plus b. By the definition of addition in any quotient ring, we have and this step comes because of the definition of addition in any quotient structure, I mean quotient ring. So you have this step, and that in turn gives the image of alpha under psi, and the next one image of beta under psi. So that's your RHS. In the same way, this one, so alpha beta plus v, and which is nothing but alpha plus v into beta plus v. So we have again the same explanation by the definition of multiplication in quotient ring. You have this step, and that in turn gives alpha psi into beta psi, and that's your RHS. So psi from f to f bar is 1 to 1 on to homomorphism. Therefore, f must be isomorphic to f bar. Also, as f is a field, f bar is also a field, and f bar is contained in E. So you conclude that E is an extension of f. See, you have considered only E. For that, what is subfield is f bar. But what is known about f bar? F is isomorphic to f bar. So from that we conclude that E is an extension of f. Now in the second claim we need to prove the degree of E over f to be n. So for that we will consider the elements in E are polynomial plus v. So we will choose the collection S as 1 plus v, x plus v, and so on, x power n minus 1 plus v. If we prove that this S is linearly independent and S spans E, then we can automatically have the dimension of, we are going to have this to be, see, from starting from 1 to x power n minus 1. So there are n elements here. Once we prove that to be linearly independent and spans, this S becomes a basis of E. E is nothing but fx mod v. So from that we conclude the degree of E over f is n. So that is the idea. Now we want to show that this is linearly independent. So the linear combination should be equated to the identity element, where from we have taken all these elements from fx mod v. So in this, identity element is v. So you have, so that is why you are choosing this, the linear combination to be equated to 0 element is nothing but v over there. So you have this. And by the definition of scalar multiplication and addition, you can rewrite this in this way, in this way. And again, one more step you can have alpha naught. You can have alpha naught plus alpha 1 x plus and so on, alpha n minus 1 x power n minus 1 plus v equals v. Again, the same concept. So from which we have this element, this plus b equals v means ha. See, we have actually corollary to this, which states that ha equals h equal to ah if and only if a belongs to h. So it is based on that. In the same way we have in vector space also. So from that we conclude that this is a member of capital V. But capital V is generated by P of x, that we have already said, and therefore we have capital V is generated by P of x. So you have this to be R of x into P of x. Now again the same concept you have on the left side degree n minus 1, and the right side you have n degree n. So that cannot happen, and therefore we must have R of x to be 0. So here again the reason is given. If R of x is non-zero, then degree of RHS is greater than or equal to n, but degree of LHS is less than or equal to n minus 1. So to avoid that, there is no other way. We need to choose our R of x to be 0. So that in turn gives, we are rewriting 0 in this way. So equating coefficients of like powers, we get each alpha I to be 0, I ranging from 0 to n minus 1. Therefore, the linear combination equated to the 0 element shows the scalars at 0, which means the collection is linearly independent. That is, S is linearly independent. Now, to prove that this collection spans fx mod v, we'll consider an element, arbitrary element, say f of x plus v in fx mod v. Then applying division algorithm to f of x and p of x. From here, you know f of x, already you are familiar with p of x. So we are going to apply division algorithm to these two so that we can find two more polynomials, say h of x and r of x, such that this result holds. Now this has to be um, from the division algorithm, this has to be written like this. Now in this you have r of x to be 0, or degree of r of x is less than degree of p of x. Now you consider f of x plus capital V. F of x is replaced by this quantity plus V, and V being generated by p of x. We can interchange these two because under addition polynomial ring is commutative. So you can rewrite like this, and this this one is absorbed over here, so you are left with this only. So you have your R of x, this is absorbed over here, so you are left with only R of x. So that is replaced by alpha naught plus alpha 1 x plus v plus and so on alpha n minus 1. In fact, we have skipped one step. You have your uh, R of x to be of degree less than p of x, means a linear combination of these two, not linear combination, a polynomial alpha n minus 1 x power n minus 1 plus b. So then you have this step, and from that you have another step, and this tells that your f of x plus capital B is the linear combination. So this is linear combination of the elements which we have mentioned in that set S. So that set is linearly independent, and it is also it also spans your fx mod v. Now so dimension, because there are n elements, we conclude that dimension of E over F, that is the degree of E over F, is n. Now in the third part we said three things that we need to establish. Now we have come to the last one, that is P of x is a root in E. So that part is to be established. So for that you consider P of x as this, and any nth degree polynomial. So you have this. Now P of x plus V will give such an expression by the addition in quotient space and multiplication. we have this step, and the whole lot is nothing but p of x plus v. So you have p of x plus v to be equal to capital V. Um, this is absorbed actually because p of x is in capital V. So taking x plus v as a, we conclude that p of a equals v. Hence, a in E is a root of p of x. So these, the smaller part of the entire theorem is this one. Writing your E, if E is not constructed in this way, then the rest is not possible. So you have to have this in your mind, that is basic. And another wonderful thing is, see, you want to have that E to be extension of F, but basically it is an extension of F closure, F bar. F bar, just F bar, which is defined as a collection of all elements of the form alpha plus b, where alpha range over capital F. So that F isomorphic to F bar, it guarantees that the elements in F bar can be regarded as elements in capital F. So that in turn enables us to conclude the E to be the extension of F. Next, we have corollary to this theorem. It states that if f of x, which is a member of fx, is of degree n, then there exists an extension E of f such that degree of E over f is less than or equal to degree of f of x in E, and f of x has a root in E. Now let p of x be a member of fx. Let that be an irreducible factor of f of x. Then degree of p of x is less than or equal to degree of f of x. We shall name that as equation 1. Now it is not equation, inequality. Since p of x is irreducible by the above theorem, there is an extension E of f such that degree of E over f is degree n, which was taken as degree of p of x. So you have that, and this degree of p of x, it's irreducible factor, so whose degree must be less than or equal to degree of f of x. And in the previous theorem again we have proved that p of x has a root in E. Hence f of x has a root in E. So that concludes both the theorem and corollary attached to it. Thank you. And on the next video we will have this theorem.